Hey, yet again, we're very excited about having you all here for the course in a couple of weeks. This week, we're going to look a little bit more in detail on the four volumetric related properties in a black oil table, and that's a very important parts of the black oil PVT model that we talked about last week. Last week, we looked at this generic overview right here, where we looked at the 7 columns that makes up a black oil PVT table, the pressures, and then for each of the components, so the surface oil component and the surface gas component, we had 3 different properties assigned to each of those at each pressure. And yet again, the assumption was that when we generate this table, we are doing that for a constant temperature. Okay. So the other thing I guess, talked a lot about in that course, and that we also got emphasized in the exercises, that black oil PVT properties are a function of the surface process. Okay, and that's typically the number of separator stages and the conditions of each of the stages. Okay, and that's if we ignore viscosity. Then we defined the different black oil PVT properties, both in terms of surface volumes and reservoir volumes. And we defined the following 4 ones, which is the volumetric related PVT properties, which are process dependent. And then we have the process independent properties, which are the viscosities. And this is what we're actually going to talk about today, these 4 volumetric PVT properties and how they, for a given surface process and a given reservoir temperature, are changing as a function of pressure. Okay. The most common probably plot of this that we've all seen most likely is oil formation volume factor, the so-called B subscript O, plotted versus pressure. Okay, the definition for the formation volume factor of oil is the reservoir oil volume divided by the surface volume of oil originating from that reservoir oil phase. Okay, the just for clarity, this is the bubble point for this particular fluid. It's around 4,500 psi or something like that. All the pressures above the bubble point are defined to be in the undersaturated region. Okay, we call that undersaturated conditions. And this is a region where the solution GOR, which we'll look at the next slide, is constant. So the composition, quote unquote, is not changing. Hence, it's just the pressure that is essentially making this into a more dense liquid, which again is decreasing your formation volume factor of oil. Okay. But when we reach the bubble point, gas starts to come out of solution. Okay. And all the pressures below the bubble point is what we talked about and defined to be in the saturated region. Okay, so this is at saturated conditions. And at each of these pressures, more and more gas is actually coming out of solution, which leaves you to have a formation volume factor of the remaining oil that's lower. Okay. The other relevant property for the oil phase is the so-called solution GOR, which is defined as the surface volume of gas originating from the reservoir oil phase, and then divide that by the surface volume of oil coming also from this, or originating from this reservoir oil phase. Okay. Yet again, just to define where the bubble point is, it's it's at the same pressure, and above this again is the unsaturated region, and we see that here the solution GOR is constant. And then as we go below this pressure, the solution GOR of the oil in the reservoir, so the oil phase, that solution GOR goes down, because gas is coming out of solution down in the reservoir. So you now have a free gas phase and an oil phase down in the reservoir. Okay, and this is how much gas is in solution in the oil phase. But then in addition, you have a gas phase that you're also producing from. So as long as you're producing above the critical gas saturation, your GORs will start typically to increase because of this also newly introduced phase, if you like, which is this gas phase. Okay. The going over to the gas side, we're typically talking about a so-called gas formation volume factor, BGD. Okay, and many places you don't see the use of a D here in the end, and that stands for a dried gas formation volume factor for gas. Okay, and we'll talk much more about the difference because there's two different definitions of gas formation volume factor, and this is the correct definition. And we'll look at the differences between BGD and the so-called BGW. And the difference in short is just that the one accounts for the condensate in solution with the gas and the other does not. And it assumes that the gas in the reservoir is a dry gas, which in general is not true. Okay, so this is the correct definition. And it's defined as the reservoir volume of gas divided by the surface volume of gas originating from the gas phase. And if you plot that as a function of pressure, you get a curve like this. And yet again, here we have a dew point. Okay, so this is the dew point in this particular case. Okay, and above the dew point, we're talking about something that's undersaturated, and below, again, we're talking about something that's saturated. However, as you see, the graphical representation of this plot doesn't help us a lot. Okay, let's say we were going to calculate gas in place, for instance, for this reservoir, and we needed, and let's say the reservoir was 8,000 psi, and we wanted to use this plot right here to actually to give us a formation volume factor of gas. It will be very hard to read off this graphically. And that's why we many times also, when it comes to gases, are talking about the inverse of this gas formation volume factor, which is just called the gas expansion factor. And it's just the inverse, just 1 over the large BGD, and it's denoted with a small b subscript GD. And we see that it's just the same, it's just a definition flipped around. The reason why it makes sense to use this is that from, at least from a graphical plotting perspective, it's much easier to actually read off the values on the plot here. Because now you see at 8,000 psi, okay, it's fairly easy for me even here, just with my own eyes, to say that this is 700 scuffs per reservoir barrel, for instance. Okay, so that's what we call the gas expansion factor. Okay, and yet again, just for clarity, this is the dew point. So now you know the difference between the gas formation volume factor and the gas expansion factor. Very good. Related also to this, so we also have a solution CGR for the gas phase. And that's defined as the surface volume of oil originating from the reservoir gas phase. Okay, so we know that there's a condensate phase in the reservoir gas, divided by the surface volume of gas originating from the reservoir gas phase. Okay, so just as the reservoir oil can contain gas in solution, reservoir gas can contain condensate in solution. And that's what this term here is representing. And in most commercial tools, if you think about Harmony, if you think about Eclipse, if you think about ResFrac or whatnot, they typically use the large R subscript V for this. So that's for vaporized oil ratio, okay? But it's the same. And the little RS is just the SPE nomenclature for the same concept, okay? So two different words for the same. Yet again, we see that above the dew point, the composition is constant, so also the solution OGR should be constant. That's what we see here. And then as we drop below the saturation pressure, we see that the OGR is decreasing until a particular minimum at a very low pressure before it actually starts to go up again. Why this is happening is something we're going to discuss in the course, and we'll leave it because it's a little bit complicated item to cover, so we'll leave it for that. But in general, you should know that this is the general shape of that curve when you decrease it below the saturation pressure. Okay. So the last thing we'll cover here, and that's a small little trick that I think it's important to emphasize, because let's say you are a geologist and or you are in the research group and you would like to map out oil in place for your entire basin. And your basin, you're in the Permian, or you're in the Eagle Ford, or you're in the Montney, or in the Duvernay, and you actually have a transition zone of both reservoir oils and reservoir gases. And if you wanted to have a consistent map of oil in place, or a consistent way of mapping, for instance, formation volume factors for both phases, you can actually define a so-called oil formation volume factor for gas condensates. We call it kind of the geologist BOI for gas condensate reservoirs. And it's very simple. And it's just taking this formation volume factor of gas, so the BGD, and divide by little rs. And what you'll see then is that the units that pop out is reservoir barrels per stock tank barrels. Okay, so reservoir barrels per stock tank barrels, and that's the exact same units as the B subscript O. And that makes a very consistent mapping of formation volume factor, for instance, that you can use exactly in the same manner as you would for a oil reservoir if you would like to calculate volumes in place, for instance. And that's going to be the topic of the exercise next week. Okay, so on that point, hopefully you've refreshed or learned a little bit new things related to black oil PVT properties and the volumetrics. And there's also an associated exercise to this a little bit later.